Introduction to Nuclear Technology. Chapter 4. Reprocessing and Recycling Discharged Fuel. During fuel's residence in a reactor, most of the initial fissile content has been consumed and only partly replaced by newly generated plutonium, while some of the fission products that have replaced it are very strong neutron absorbers. Consequently, its reactivity falls towards a point where maintaining the reaction would be difficult. Moreover, the intense neutron bombardment has to some extent distorted and weakened the physical structure, which may also be under internal stress from the pressure of fission product gases. Nevertheless, the fuel still retains nearly all of its fertile content, uranium-238, and often a U-235 content still higher than natural. To discard these is considered by many to be reprehensibly wasteful. On the other hand, it contains fiercely radioactive fission products, still emitting as heat a significant proportion of the energy released by fission, as well as transuranic elements in amounts superproportional to the neutron irradiation undergone. The greater the number of neutrons involved in their generation, the greater the superproportionality, although because of other factors it is not a direct mathematical power relationship. Thus, although the fuel still has the potential for many times the energy generation already achieved, there are substantial obstacles to realizing that potential. Management options after decay storage. Reactor operators have two choices: disposing directly of used fuel or having it reprocessed to recover useful materials. In the short term, direct disposal is the easier option, involving a minimum of relatively straightforward operations. It also minimizes any risk of illicitly diverting fissile material to improper use. On the other hand, it leaves the plutonium content intact, with diminishing self-protection as fission products decay, arousing fears that a repository might, in time, become a plutonium mine. Because no chemical operations are involved, secondary wastes are minimized. However, it means abandoning about 99% of the energy potential in the uranium that went into its manufacture, including the large proportion now remaining as depleted tails from the enrichment process. Reprocessing, on the other hand, is a major and expensive industrial operation. It recovers fissile and fertile material for future use, although they require fast reactors for full utilization. In thermal systems, the improvement is limited. It permits the eventual destruction or degradation of weapon-usable material. It minimizes the volume of high-level waste, but produces a great deal at lower levels. Reprocessing is conducted at only a few sites distant from most reactor stations. On discharge, the fission product content of the fuel emits far too much heat to be tolerable in transit, and a period of local storage is needed to let it decay to an acceptable level. Even then, the transport containers, flasks, need provision for dissipating the remaining heat release, and further decay storage is usual at the reprocessing site. In reprocessing, the uranium and plutonium are separated from the fission products and each other, then converted into suitable forms for storage. The fission product wastes are stored in solution to allow further decay, and eventually conditioned for disposal, which, except at low level, has not yet occurred. Delay storage. This may be either in water-filled ponds or air-cooled vaults. In ponds, water both cools the fuel and shields operators from radiation. Fuel containers remain directly visible, simplifying any manipulation that may be needed. However, the weight of water demands a very robust and seismically qualified structure, especially if it is raised to allow direct monitoring for leaks. The water must be continually purified from algae and activated corrosion products to maintain visibility and shielding. The working atmosphere tends to be uncomfortably humid. On the other hand, dry storage avoids corrosion, especially of magnox, avoids the need for water purification, allows tighter packing without risk of criticality, but requires remote manipulation, and so needs more complexity in building design and handling equipment. And finally, it needs guided convection or continually forced air cooling to prevent overheating of the fuel. Transport flask requirements. During transport, it is essential to maintain adequate shielding, especially against neutron and gamma radiation, since the route passes through areas accessible to the public. Containers must be capable of dispersing the maximum heat load without undue rise in temperature. In particular, they must be able to withstand the severest credible accident conditions without exposing the fuel, leaking contaminated water, or losing shielding. This last point was tested by crashing a 100-mile-an-hour locomotive into a static magnox flask, which suffered only superficial damage. However, there have been questions since of whether that was actually the most severe credible accident. Transport flasks. Magnox and AGR fuel elements are relatively short, and so are transported in roughly cubic flasks. Light water reactor elements are very much longer, and so are carried in horizontal cylinders. Both types are equipped with cooling fins. The fuel storage pond at the thermal oxide reprocessing plant at Sellafield. This plant was needed because although the principles of chemical separation are the same in both magnox and oxide reprocessing, the mechanical operations beforehand are quite different. Reprocessing principles. The stages of reprocessing are separating the fuel substance from the cladding, dissolving the fuel substance in nitric acid, if this has not been the means of separation, extracting the uranium and plutonium into diluted TBP, separately backwashing the uranium and plutonium into more dilute nitric acid, purifying them and converting them into suitable forms for storage, and finally concentrating and storing the wastes for eventual disposal. The separation from cladding differs according to the type of fuel. Magnox, a thick uranium metal bar encased in a relatively soft magnesium alloy, is rammed through a die to peel off the alloy, which is discarded as intermediate level solid waste, rather than itself going into solution with the uranium and eventually adding to the high level inventory. Oxide, by contrast, comprises small ceramic pellets contained in narrow tubes of stainless steel or zirconium alloy not amenable to such treatment. Instead, the tubes are chopped into short pieces and the fuel content dissolved out with nitric acid, to which the cladding is inert. Outline of the chemical separation process. Purex. The standard Purex process is basically very simple, although variants and complications are possible. As in the purification of uranium received from the mine, the fuel solution in fairly strong nitric acid is contacted with diluted TBP, which extracts not only the uranium, but rather less readily the plutonium. Left behind are all but traces of the fission products, which are the essence of the high-level waste. Although plutonium in its most stable form is less extractable than uranium, the difference is not great enough for a clean separation when the two are back extracted into dilute acid. To enhance it, the plutonium is chemically reduced to a very much less extractable form. The difficulty is to keep it so, but that's a more complicated business than we need go into here. Finally, the uranium is separately backwashed into very dilute acid. Both products are further purified and converted to suitable forms for storage. The solvent used in the process suffers some damage from radiation or chemical attack, and before recycling is chemically washed to remove the degradation products that would tend to extract fission products or interfere with the mechanics of the process. Process requirements are very strict. The first is on safety, both operational and environmental. Despite prolonged cooling of the fuel after discharge from the reactor, it still emits intense radiation. Two of the major fission products, strontium-90 and cesium-137, both have half-lives of about 30 years, and so remain intensely radioactive, consequently requiring extremely rigorous containment and shielding. With plutonium-rich fuels, another crucial requirement is to avoid any possibility of criticality, which would emit an intense burst of radiation. In order to allow handling without special measures, the product specification requires that the fission product content be reduced by a factor of 1,000,000 to 100 million. This is not easy to achieve in a single process cycle, and at least two are needed, generally differing somewhat in function. Degradation products of the solvent can seriously detract from separatory efficiency, so solvent purification is an important part of each cycle. Finally, wastes must be manageable within strict regulatory limits and without too much difficulty or expense. This is a major consideration in determining the configuration of the plant and the detailed chemistry employed. In this respect, the significant stage is the reductive backwash of plutonium. The Magnox plant was designed to use as chemical reductant ferrous sulfamate, which is very effective, but leaves a waste loaded with corrosive iron salts and sulfuric acid that would be very troublesome to store. The intention was therefore to allow its fission product content to decay below the limits for discharge to sea, then much less restrictive than they have since become, and dispose of it in that way. The overwhelming majority of the fission products, notably strontium-90 and cesium-137 with their roughly 30-year half-lives, therefore had to be eliminated before the uranium and plutonium were separated, and this was done in a preliminary co-processing cycle. By the time the oxide plant came to be designed, restrictions on waste discharges had become much tighter, and the cost of a preliminary cycle was also a serious issue. The decision was therefore taken to avoid as far as possible using any reagents that would leave extraneous salts in a seriously radioactive waste, and thus prevent concentration to very small volume for storage before being eventually incorporated into a form suitable for final disposal. Instead, tetravalent uranium, that is, in an unusually low oxidation state, would be used, and when oxidized would simply join the uranium product rather than following a waste stream. The uranium and plutonium could therefore be separated in the first cycle before individual purification and finishing. One thing that can seriously interfere with plant performance is solvent degradation, mostly due to the effect of intense radiation in the presence of nitric acid rather more concentrated than the usual dilute reagent in a teaching laboratory. Both extractant and diluent are affected in different ways and on different timescales. Short-term degradation concerns chiefly the tributyl phosphate extractant, detaching one or two of the butyl groups, forming dibutyl and monobutyl phosphoric acids. These tend, respectively, to retain metal salts in the solvent phase during backwashing and to generate precipitates with some of the fission products. These acids are removed fairly easily by the alkaline wash that forms part of the solvent purification in each cycle. Longer-term degradation affects the diluent, forming a wide range of more or less oxygenated compounds such as acids, ketones and nitro compounds. These are only partly removed in the solvent wash and tend to accumulate, hampering separation of solvent and aqueous phases after mixing, and also impairing decontamination. They may be controlled by continually bleeding a portion and replacing with fresh, with an occasional complete change of inventory. Countercurrent operation. Solvent extraction is not an all or nothing process, but the approach to an equilibrium between solute concentrations in the two phases under conditions designed to favour one or the other. Achieving more or less complete transfer requires many stages through which the solvent and aqueous phases pass in opposite directions, countercurrent flow. Thus, in forward extraction, the fresh solvent meets an almost exhausted feed solution to take out some of the remaining traces. Conversely, the fresh feed meets solvent that has already reached a high loading and pushes it even higher, as is important to squeeze out impurities that have some affinity with the solvent. To reduce such unwanted extraction even further, some scrub stages are commonly added so as to contact the loaded solvent with a relatively small flow of clean acid that subsequently joins the main feed. They also take out a haze of fine aqueous droplets, too small to separate previously. In terms of actual equipment, the chief requirement is to ensure that solvent and aqueous phases are thoroughly mixed within each stage, but not between stages. These may either be physically distinct or merely theoretical subdivisions of a vessel through which the liquors flow continuously. Physically distinct stages are represented by the mixer-settler banks used in the Magnox reprocessing plant. In each subunit, the solvent and aqueous phases are brought almost completely to equilibrium, then allowed to settle, with the solvent going to the next stage in one direction and the aqueous solution in the other. Such plants are easy to design, and their performance can be predicted with an accuracy limited almost entirely by that to which the equilibrium conditions are known. They are largely self-regulating and can tolerate wide variations in throughput with little effect on performance. Their chief disadvantage is the time taken to settle at each stage, exposing the solvent to correspondingly high radiation doses and implying a very bulky plant with a large inventory of material held up in it. Moreover, the risk of criticality limits their use for fuels of high plutonium concentration. The Dounreay plant for fast reactor fuel had a different geometric layout, with narrow units set up in line rather than parallel, and a relatively low throughput. To meet these objections, pulsed columns were chosen for use in the Sellafield oxide fuel plant, Thorpe. These are essentially vertical pipes divided by many perforated horizontal plates to limit longitudinal mixing, with liquors forced through the perforations by a periodic pressure pulse. Settling is allowed only at the top and bottom. Residence times are much shorter than in a mixer settler, and the geometry allows much of the radiation to escape rather than be absorbed within the unit, so solvent degradation is greatly reduced. More importantly, fuels of high fissile content can be accommodated, especially if the pulse plates are loaded with a neutron absorber such as boron. Except perhaps in the settling zones, the solvent and aqueous phases should never be at equilibrium, since there would then be no mass transfer between them, and that region of the equipment would be wasted space. Consequently, performance is hard to predict at the design stage, depending on residence time and transfer rates that in turn depend upon the distance from equilibrium and factors such as the size of droplets and the internal circulation within them. It is consequently liable to vary greatly according to conditions. Control is also a substantial problem. The height and the need for seismic qualification means an expensive containment building, while residence time is still longer than might be desired, and it seems likely that any future plant would revert to a kind of mixer-settler system with centrifugally enhanced settling to minimize hold-up. Waste management principles. One of the most troublesome issues in reprocessing is managing wastes. Unlike, for instance, sorting coins by denomination, no chemical separation is ever absolutely clean-cut. Although the bulk of the fission products remain behind when uranium and plutonium are extracted, some significant traces are carried forwards and later emerge from purification stages. As far as practicable, all wastes are stored in solid form for security, but some, such as iodine and krypton, are difficult to confine reliably. The view is taken that within strict limits it is better for everyone to receive a small radiation dose than to risk high local uptake through failure of containment. The small dose may actually be completely harmless. The assertion that no level of radiation is completely safe is a statement of belief rather than of verifiable fact. Accordingly, such volatile elements, along with others at such low concentrations that they cannot sensibly be separated, are dispersed to the environment. All but a trace of the original fission product content of fuel ends up as solid at 4 levels of activity. High level, so radioactive that heat release is a serious consideration in disposal. Intermediate level, substantially radioactive, but not enough for heat release to be troublesome. Low level, low enough for shallow burial. And very low level, disposable with general rubbish. It should be remembered that all materials in common use or the environment, including our own bodies, are naturally radioactive to a slight degree, and in that sense there is nothing new about such disposal. Waste management at Sellafield. As much as possible of the fuel's radioactive content is confined to a small volume of glass as high-level waste, and the intermediate-level waste immobilized in cement, both for disposal deep underground, although separately, as they are chemically incompatible. It is assumed that a repository would sooner or later be flooded, a point apparently overlooked in much of the argument about choice of site, and high-level waste requires conditions that, if anything, are acidic, while the cement encapsulation of intermediate-level waste would release alkali. Low-level waste solid is packaged in secure containers for near-surface burial. Krypton is discharged to the atmosphere, iodine as far as possible to the sea, where except locally most radioactivity is due to natural potassium-40. Such discharges must be kept as low as reasonably practicable. The different levels of radioactive solid waste are in fact different materials. High-level waste is essentially the fission product and minor actinide content of the fuel, together with corrosion products from the cladding, incorporated into borosilicate glass. Intermediate level waste includes fragments of fuel cladding, plutonium-contaminated materials, resins and sludges from effluent treatment. Low-level waste is domestic-type rubbish from active working areas and offices, only may be contaminated, lightly contaminated laboratory equipment, and so on. Very low-level waste is similar, except that in the circumstances of its generation it could not be significantly contaminated. Low-level liquid is predominantly the treated effluent from cooling ponds, plus, for instance, condensate from the evaporation of higher-level liquors. Degraded solvent taken from the separation plant does not appear as such in the final wastes. It is destroyed by reaction with caustic soda solution, which takes out practically all of the radioactive content, leaving two relatively clean components: sodium dibutyl phosphate that can safely be discharged to sea, and a mixture of kerosene and butanol that is burnt. The contaminated alkaline solution joins others for clean-up and eventual discharge within strict limits. This cutaway model of a highly active waste package was provided by the French equivalent of BNFL at a meeting some 20 or 30 years ago. I don't remember precisely when. It was said to represent the waste from the generation of electricity sufficient for 20 years in an average French family of the time. The Sellafield scheme of managing liquid wastes in the mid-1900s shows the effect of incremental changes over nearly half a century. In the early days, the salt streams, with too much dissolved solid to be concentrated for indefinite storage, would have been discharged to sea after a fairly simple treatment to remove excessive radioactive content. Except near the point of discharge, the overall radioactivity would have added little to that due to the natural potassium-40. But progressively stricter regulations required tightened procedures, especially for alpha-emitting nuclides and the water from fuel storage ponds, with a good deal of backfitting new equipment. The process has continued since, notably with a new process to remove technetium after complaints that discharges were threatening the livelihood of Lofoten Island fishermen, whose produce commanded a premium in Japan. Product finishing. For storage, both uranium and plutonium are converted to oxides. Uranium by denitration, and plutonium by way of the oxalate, which provides an extra stage of decontamination. Product recycling. After passing through a reactor of current commercial types, uranium has yielded only about 1% of the energy theoretically obtainable from that which went into its manufacture, including the large proportion that ended up as depleted tails from the enrichment process. Supposing fuel to be of a normal uranium oxide type from a pressurized water reactor, after irradiation to 40 megawatt days per ton, the assumptions embodied in the design of the Thorpe plant, its main constituent is some 96% of the original uranium. It still has more than the natural uranium-235 content, but also uranium-234, a non-fissile neutron absorber, and U-232, which is troublesome in generating rather quickly a decay product, thallium-208, that emits exceptionally energetic and penetrating beta-gamma radiation. About 3% of the original uranium-238 has been converted to plutonium, and of that about 2/3 has undergone fission. The first isotope formed is plutonium-239, but continued exposure to neutrons generates plutonium-240 and 241 in amounts superproportional to irradiation. Only the odd-numbered isotopes are fissile, but all are fissionable in a fast neutron flux, as indeed, though less readily, is uranium-238. Spent nuclear fuel and depleted uranium tails thus represent a potential source of far more energy than has already been realized. Most reactors currently operated are not suited to plutonium-enriched fuel, while the presence of the artificial isotopes renders the uranium less attractive to manufacturers than fresh material. Nevertheless, at least 15,000 tonnes have been recycled in the UK alone. Newer designs can take plutonium, and with recycled uranium as well, could increase the yield by about 30%. However, the real benefit is to be expected from fast reactors, breeding fresh plutonium from depleted or recycled uranium, which, even allowing for various inefficiencies, should increase utilization by a factor of about 50. Refabrication of uranium fuel is essentially the same as the original manufacture, except that re-enrichment concentrates the undesirable isotopes so that precautions against radiation exposure are likely to be necessary. The greater efficiency of centrifugal enrichment compared with diffusion means that a dedicated plant could probably be set up for the purpose. An alternative possibility is to recycle spent fuel more or less directly in reactors of the CANDU type, which with their high neutron economy need less fissile content than is required with light water cooling and moderation. In fabricating plutonium-enriched fuel, the essential requirement is homogeneity, to avoid hot spots under irradiation that might lead to premature failure of the cladding. Co-precipitation, which might seem the obvious way to achieve uniform distribution, needs special measures to prevent the plutonium from coming out of solution first, and dry blending, despite its various disadvantages, may be preferred. Safeguards. A major concern throughout the history of nuclear energy has been to ensure that material, especially plutonium, intended for civil use, is not diverted into the production of weapons, crude or sophisticated. For this reason, accountancy of nuclear material is a very serious undertaking. The term is unfortunate in that it suggests a comparison with financial accountancy, where in principle there ought to be no discrepancy between expectation and reality. With nuclear material, this does not apply. Numbers of discrete items, such as fuel elements, can be checked against records and should agree exactly. But calculations of plutonium generated and measurements of quantities in process are all subject to uncertainties, for instance, due to the limited precision of analysis. Discrepancies are recorded rather misleadingly as material unaccounted for, which may be a positive or negative figure. This does not mean that material has gone astray or been surreptitiously imported, rather that it never existed in reality or has been generated in rather greater amounts than the data imply. Accountancy in this sense is therefore a means of verifying that material has gone where it was supposed to go, and that the measures of physical security have achieved their purpose. For the future, a principal driver is the desire to reduce waste arisings and costs at source. The trend in reprocessing is therefore likely to be simplification. Thorpe achieved a considerable degree in comparison with the Magnox plant by reducing the number of cycles from 3 to 2 for each product. Reducing it further to a single cycle would be of great benefit, But unless there were a greater improvement in the already very high separation efficiency than seems likely to be achievable in practice, it would mean a trade-off with the increased difficulty of handling, storing and refabricating the products. One way to reduce costs, especially of the buildings to house the processors, is to reduce the size of equipment used for a given throughput. Intensification. Continuous rather than batch dissolution is one possibility, though past attempts in that direction have run into mechanical problems and there may be issues in accountancy. Prospects are probably better for centrifugal solvent extraction contactors. For small amounts of special fuels, there is much interest in pyrochemical processes, generally involving electrolysis in molten salts. Such schemes would be especially suitable for integration with molten salt reactors. Finally, there has been great pressure to separate high-level waste into various fractions, long-lived, heat-releasing, etc., as will be described in Chapter 5. Future recycling technology may be expected to be progressively more radical. Chemical processing generates the most troublesome wastes, but might be avoided, at least temporarily, by the direct use of PWR fuel in CANDU system. Here the fuel pins, about 12 feet long, are cut into 50 centimetre pieces, resealed and assembled in the CANDU arrangement. Alternatively, the fuel may be heat treated to release volatile products before repelleting and assembled in the normal manner, except that of course it would all have to be done remotely behind heavy shielding. To avoid the difficulties of pellet formation, powder prepared by gelling and calcining droplets of a mixed uranium-plutonium solution might be vibro-packed directly into cladding tubes. However, it has proved difficult to ensure uniform packing and avoid hotspots that could threaten the integrity of the fuel. For the more distant future, there is a particular interest in molten salt mixtures, in which uranium and plutonium compounds are soluble. Much work has already been done on reprocessing in such mixtures, generally by electrolysis, with an obvious attraction in the possible symbiosis with molten salt reactors.